Okay, in the last video we calculated the fuel to air ratio. So in this video we're going to calculate the temperature and pressures at the output of the turbine. So if we take the high pressure turbine first, which is this part here, we know that the work done on the high pressure compressor here must be the same as the work taken by the high pressure turbine multiplied by some efficiency factor. This is the mechanical efficiency due to losses on the shaft here, bearing losses, frictional losses, and so on. Okay, so we can expand out that equation. So the work on the high pressure compressor is the CP of air times T5 minus T4, T5 minus T4. So that's the work on the high pressure compressor. And on the high pressure turbine, well, the mass has changed. So there's a mass of air coming through, and then we added in some fuel. So the mass out here now is the mass of the air and the fuel. So this 1 plus the fuel to air ratio, that's how we account for that there. There's the efficiency, and there's the work done on the turbine. So it's the specific capacity of the gas. The difference between gas and air is this is just pure air, and this has air and the spent fuel in it. Okay, basically the exhaust gases. So there's the equation again. When I just move that around, I am left with this. Basically I've divided this side here by that part, and plug in the numbers. So we had T6, and we had what the specific capacity of the air is. We had T5, we had T4. The mechanical efficiency of the shaft, we're given that. And the fuel to air ratio, we calculated that previously, and specific capacity of the gas was given to that. When we plug all those numbers in, we get 975 degrees Kelvin. Okay, I then use that temperature here, that 975, to plug into this formula, and we derived this formula in a previous video. And just plugging those numbers in will give me the pressure at the outlet of the high pressure compressor. To work out the pressures and temperatures on the low pressure turbine, we have to go back to this formula. So whatever work is taken from the low pressure turbine, that is used to drive the low pressure compressor here, and the fan, this here. So when we expand that out, well, the work on the fan, we have to be mindful that the mass of air going through the fan is the mass of air going through the core of the engine plus whatever air goes around the engine, the bypass air. So if we add the bypass ratio to 1 multiplied by the mass of air going through the core, we'll have the mass of air going through the fan. So multiply that by specific capacity of the air times the temperature drop across the fan, and then this is the work done on the low pressure compressor, and this is the work done on the low pressure turbine multiplied by the efficiency, the mechanical efficiency of the shaft. Okay, so the masses all cancel out, and if I divide across by 1 plus F, I'm left with this, 1 plus F here, 1 plus F, 1 over 1 plus F here, and then I divide across by the mechanical efficiency. So that goes in here. Actually, I divided by the mechanical efficiency and the specific capacity of the gas. And now on the next slide, that's what we had. I'm just going to bring T8 over to here and all of this expression to the right hand side. So now I have an expression for T8. I'm going to plug in those values, and I get a value of 615-ish degrees Kelvin. I go back to this formula for the output of a turbine. We used it on the low pressure turbine, high pressure turbine, so we can use it here on the low pressure turbine. Same formula, just different values. So I'll plug in the numbers, and I get an output of 43.83 kilopascals. Okay, so in the next video we look at the nozzle.